And up next, we have Ashton Danehkar, who is a postdoc at the University of Michigan. And he will be talking to us about emission lines from Superwinds of superstar clusters.
Hello, good evening. And today I will talk about my recent hydrodynamic and photoionization result of the superwind simulation from which driven by superstellar clusters. Superwind and the superbubble typically observed in the starburst in galaxies, and this superwind is driven by thermal and radiation feedbacks from OB association and the supernova explosions. In some of the superwinds, some of the starbursting galaxy, we see the suppression of the superwinds and also strongly radiative coolings, which cannot be explained clearly. And in this work, I did hydrodynamic simulations of superwind and super bubbles. These hydrodynamic simulations is based on the Advetics analytical solutions by Chevalier and Kellage, which developed in 1985. And later, the radiative solution developed by Silich in 2004, in which they included radiative cooling solutions. Here you see the difference between adiabatics and the radiative solution, and you see the higher metallicity contribute to a strong cooling in this cooling curve of superwind. And here is the typical profile, density profile, and temperature profile of superwind and superbubble. Here we have a bubble which is produced by its temperature of 10 million kelvins, and here we have a shells. And here is the result of the hydrodynamic simulations. In the low velocity, you see the suppression of superwind and the catastrophic coolings, but in high velocity, you see the formation of the temperature bubbles. And I did a parametric investigation. I ran a series of grades for different mass loss rate and different ambient density and metallicity and velocity. And in this example, which I show here, we see the catastrophic cooling happens in the high metallicity and low velocities. And CC is catastrophic cooling, CB catastrophic cooling with bubble, and ABAC is adiabatic solutions. And I did a photoionization with cloudies. And here you see the optical solutions, and we see they are overlapped with region, which observed as a star-based regions. And I also extract UV emission lines, which you see here. And you see how UV emission line change by metallicity, ambient density, change of ambient density, and change in velocities. And this cross and plus is associated with catastrophic cooling, anti-catastrophic cooling with bubbles. And we see how the change in metallicity and change in ambient density contribute to the formation of catastrophic coolings in these hydrodynamic simulations. Also, there is other line. Also, I extract this for radiative bounded model, and also extracted for partially density bounded model, and you see the change variation in UV emission lines by difference metallicity and ambient densities. And the other thing is important is oxygen 6, because in one observation they observe oxygen 6 in starburst regions, in nearby starburst regions, and here you see with how the change of metallicity contribute to formation of catastrophic coolings. And you see a diversion from typical pattern because of catastrophic cooling, because of the strong radiative cooling. This model which have catastrophic cooling, they don't follow the typical patterns. And this is a summary of my talk. I talk about how we did hydrodynamic simulation, which is analytically solved by Chevalier Kellage. Also, we include radiative cooling, which analytic solution developed by Silich in 2004. And we did parametric investigations of the catastrophic coolings by changing metallicity, mass loss rate, and wind velocity. And we see in higher metallicity and low velocity, we have the formation of strong radiative coolings. And I produced, by using Kaladi model, I produced the PPT diagram and UV diagnostic diagram in order to help to diagnostic which region we have catastrophic coolings. Thank you. If you have any question, I can answer.
All right, thanks for that. Let's see if there's any questions on the chat. Okay, so I have a question. We have plenty of time. So I'm, of course, superstar clusters is not my area of research. So I'm wondering how much optical data does there exist that these kind of models can be applied to? Is it really common to have all of these different lines for different superstar clusters?
Yeah, here you see this optical data is from this 4 paper. It's from Green P analog and Starburst Galaxies. But this optical is integration over whole galaxy. So we may not able to see the catastrophic coolings in this optical sample, but we can use the UV data to see which one is associated with catastrophic cooling, because typically with those catastrophic cooling, we have higher carbon 4s and also we have oxygen 6. But in optical data, there are those starburst regions. As you see, there are overlaps with those starburst regions.
And it looks like from these diagrams that you can't really diagnose metallicity. The metallicity lines all seem to cluster around each other.
With change in metallicity, it's contribute with, no, yes, in optical, no. But in the UV, you see the change in metallicity contributes to higher cooling. So oxygen 3 reduced, oxygen 3 over helium 2 you reduce by increasing the metallicity, because increasing metallicity contribute to cooling effects. But in optical, yes, optical is a bit difficult. But in UV, yes, we see the change in metallicity reduce oxygen 3.
Right. And so what are your, so with this model and these diagnostic diagrams, like what are your next steps in this project?
The next step is here you see we have cross and plus, which is associated with suppressed superwinds because of strongly catastrophic coolings. Here I show. Yeah, here you see the suppression of this bubble. This bubble, temperature bubble, is not forming. And the next is we should find a way to see how we can use these diagnostic diagrams to identify this formation of suppressed wind or catastrophic coolings.
Mm.
As you see here, in this region is not catastrophic, but when there is catastrophic cooling, there is a reduction in carbon 4, and so it's shifted to left. Also, similarly for this metallicity, shifted to left because of strongly radiative coolings. It's reduced oxygen 4. No, it reduces carbon 4.
Okay. All right. Well, that was really interesting. Thank you so much.
Thank you.
Okay, so our next